keeping equations balanced. Each of these tug-of-war teams has the same total mass. So when I have the same total mass, we're going to assume that they also have the same strength. So these 5 people, as they pull, is going to have the exact equal amount as these 5 people. So we can picture an equal sign in the middle of them right now. And so kind of like the teeter-totter that we had in the last lesson, this is nice and balanced. And so in theory, these guys are going to pull and pull and pull until everybody's tired and everybody just gives up. Now, if Team A also gets this girl who is 48 kilograms, what would we have to do in order to keep this match fair? So if I added 48 kilograms over here, we would assume that all of a sudden A would win. Just like in my balance beam, the boy would go down with his backpack. So what could we do to keep that balanced? And so when we think about that, it makes sense to say either the girl's going to put her backpack on as well, or we will have another person also join this team B that is 48 kilograms. So Max started with this equation each time. So 2 plus 4 equals 3 times 2. So here he's got some counters. So he has 2 plus 4 and 3 groups of 2, which is how we would represent 3 times 2. Each side here has 6 counters. Now, if he takes 4 of the counters away from the left-hand side, it's not equal anymore. So in order to keep it the same, he has to take 4 counters off of this side as well. We can do this with all the different operations, and you'll notice that if we want to keep that balance, or we want to keep that even teeter-totter or the stalemate in our tug-of-war, we need to do the same thing each time. So here he starts with his 6 and he added 2 to each side. Well, now we each have 8. Here he multiplied each side by 2. So instead of having just 6, he has 2 rows of 6, which is going to be 12, and 2 rows of 6, which is going to be 12. And in the last, he divided each side into 2 equal groups. So he has 2 groups of 3 and 2 groups of 3. So whatever Max did to one side of the equation, he did to the other side too. Each time, the numbers of the counters remained equal. So the equation remained balanced. So if we think about those balance scales and we're talking about equations, that's our goal, is that we always want to do whatever we do to one side, we're going to do to the other side as well, because that balance is super important. When each side of the equation is changed in the same way, the values remain equal. This is called the preservation of equality. So preserve means to keep, and equal means the same. So we want to keep the sameness. The same is true if one side of the equation is an expression containing a variable. So if 6 is equal to 3t, we could show this with paper strips. So I have 6 and it is equal to 1, 2, 3 t's. And so to preserve equality, we can do the same thing that Max did with his counters. If we add 1 to the 6, we also have to add that same amount with the t's. If we subtract 1 from the 6, we would have to cut off the same amount on the t in order to stay equal. So we'd have 3t minus 1. We could multiply. So if I have 2 6s, then I'm going to have 2 times 3t, which would work out to being 1, 2, 3, 4, 5, 6t. And I could divide. So if I divided or cut that 6 in half, I would have to cut the 3t in half as well. When we do the same to each side of the equation, we produce an equivalent form of the equation. So what that basically means is that all of these equations that we created, 6 plus 1 equals 3t plus 1, 6 minus 1 equals 3t minus 1, 2 times 6 equals 2 times 3t, and 6 divided by 2 is equal to 3t divided by 2. All of these are equivalent forms of the equation 6 equals 3t. So much like the last section, I could rewrite any of these together and they all mean the exact same thing. They all represent the same amount. They're just lots of different ways that we can sort of dress it up to describe what it looks like. So there are some questions here for you to practice with. If you do not have, it does talk about counters. If you have counters, that's awesome. If you don't, you can use colored pieces of paper or Lego or anything really that you have a whole bunch of in your home. You could use coins. Those are all really good things that you can use to sort of physically manipulate these things. And a big thing that we're going to look at is moving from doing it physically with counters to drawing it and then to using symbols. So when we're looking at the difference, I actually haven't shown you the concrete way, I've shown you the picture way. So if I would actually have these counters sitting in front of me and I was touching them with my hands, that would be the concrete way, or the counter way that it asks you to describe it. What you see here with the pictures of the counters or with the strips of paper, that would be a diagram or a picture way to show your work. And then symbols would be these equations. And so that would be the 3 different ways that you can show and that you should try and work and practice representing each of these by.